Hey, this is Brock Lemires, and in this video, I'm going to talk about the history of the C programming language and also the anatomy of a standard C source file. Okay, so it's always good to learn just a little bit about the history of a language, and really it's to put it in context of some of the naming conventions that you see, and also kind of some of the features that were first developed. So the C programming language was actually invented or created in 1972 by a gentleman named Dennis Ritchie at Bell Labs. So Bell Labs was a research facility that created many of the modern modern inventions that we have, transistors and such. But it was actually it was developed as a way to create utilities, software utilities, for an operating system that was called Unix. Unix, this is not Linux, this is Unix. Unix came out in the 60s, and it was one of the first successful operating systems. So before that, this is going back before integrated circuit CPUs, right? So this is, we're talking about vacuum tubes, and, everybody who built computers was trying to put some sort of software on top of it, but Unix was the first one that was kind of like a general operating system. Now, for perspective, the 60s, that was pre-mouse, right? So there was no such thing as like a graphical user interface. This was the dark console, basically what we're doing today. And Unix was rewritten later to become Linux so that it was more open source, but Unix was the first one, okay? Unix, it's important to note that Unix was written in assembly, okay? So remember what assembly is. That's where you program a computer instruction by instruction, and the only abstraction that you get is instead of like typing in the binary code for an instruction, you can use a mnemonic label. So instead, if you wanted to load something into a CPU register, you might be able to say LD or LD into A or something like that, but very, very low level. So imagine trying to create an operating system at that level. Okay, and that's important because later, what they tried to do with this language was they were trying to abstract like just basic things. So you have Unix, which is written in assembly, and they want to just do standard things, data processing and hooking to input and outputs. And they were like, man, it is really tough to write in assembly. So I just want to have some language that's a little bit higher level so I can use things like, data types and decision statements and program control. But I don't want to be super high yet, right? I want to be really low level because it's really just translating, a more abstract text description of a functionality into the assembly language instructions. So that's why C is such a low level language is what they call it. So there's another guy, Brian Kernighan, and he encouraged Dennis Ritchie to write a book on the language C that came out in 1978. Now, why do you care what these guys' names are? It's because a lot of times you'll see this documentation of the first like C programming book as calling the language KNRC. So KNR stands for this guy's name, Kernighan, and then R stands for Ritchie. So that's where KNR came from. And then later, like with all things that become popular, everybody had kind of their own version of it. So then in 1989, it became adopted and standardized by this organization called the American National Standards Institute, or ANSI. And so right around then, you started hearing it called ANSI C, and that, or also called C89. And that was just basically a standardization of the language where it was like, okay, this is the agreed upon set of functionalities that this language will have. A year later, in 1990, another kind of standardization institute called the International Organizations for Standards, or ISO, adopted C. And it came up with its own standard, which was exactly the same as ANSI C. It's just a different standardization body. And that was called ISO C. And that was called C90. Okay, so it was actually called C90. The important thing about all this stuff is that ANSI C is the same as ISO C, is the same as C89, and that's the same as C90. So this should be C90 right here. And that's just, okay, they're all the same language. But if you look at then kind of the timeline of other standards that came along, there was another revision in 99 called C99, another one in 2011 called C11, another one in 17. And then there's always one coming in every year that it doesn't come out. They just increment the year. But anyway, these are just, every time they standardize it, they add a little bit more functionality, a little bit more functionality. And so that's the history of C. It's been around for a long, long time. It's very powerful because of how it was designed. It was meant to be like just one click above writing an assembly. So we call this low level. and it accesses the computer hardware at a very low level. Like it is really like accessing addresses in memory directly. You can even have it put information directly in a CPU register. So as we learn about this, you're gonna talk about like, I'm gonna grab the address of a specific location and I'm gonna use that address later, or I'm gonna use that address and then add one to it to get to the next location. So you're really, really low. Okay. The other thing it gives you is the ability to specify the encoding techniques. So if you're gonna store information in memory, I mean, you can tell it, hey, encode this as an integer, or encode this as a character, or encode this as a real number. And so that might sound silly, but if you think about it, in the beginning in assembly, you basically were just typing in binary bits, and it was up to you to figure out whether the bits were representing a character or an integer. And so this was like the first time where you said, okay, you're going to have data types, and we give you the specifics of exactly how they're encoded. It's also good though, because later on languages became very high level, and what high level means is that you abstract the computer hardware from the programmer. So the programmer doesn't even care about what type of memory or how much memory there is. They're just like, put it all in memory. I don't care. I'm sure I won't run out. And they don't even specify like what it is. Like you can just say A is equal to Brock, and now A is equal to 22, and the compiler and the software just handles it for you. And that's very abstract. You lose control of the lower level of hardware. C is not that. Okay. One of the good things about C is that since it's implemented at such a low level, very, very basic of like, you have memory, it has an address, it has a value, and it's got binary bits encoded like this. It makes it portable to many different computers. When you abstract computer hardware, you have to write a lot of complexity in order to hide what's actually going on in the box from the programmer. So the programmer doesn't care, life is good, I'm just writing my code, but that code doesn't move to another computer architecture without having a great deal of software in between to hide what's happening on the next computer. Okay. And then of course, C is fast, right? Because it's only one click above assembly. And so if you have a very high level language that hides all the computer software or the computer hardware from the programmer, that's other stuff that has to run, right? And so there's a lot of bloat in between what the programmer types and what actually gets implemented. In C, you're right down at the memory and register level. Okay. All right. So that's good. Now, today, C is still one of the most popular programming languages in use, and it has been since it came out. So, I mean, 1980s and 90s, everything was written. Linux was actually written in C, okay? And we use it today. Today, it's really driven by programming what we call embedded computers. So when we talk about the Linux server, that's a big server, lots of memory and operating system, etc. But think about all the computers that are in your life, like a microphone that I'm talking into, or the thermostat on the wall, or your TV. All of those have computers in them. All computers run software. And when you have really small computers that have a dedicated task, you don't want to install a huge operating system on it. You just want to run instructions. So that's what C is used for primarily today. C is used for everything, but it's almost exclusively used when we program embedded computers. When you look at the follow-ons for this class, you're going to use C. So when we talk about, okay, now we're going to program a microcontroller in embedded systems to spin motors and control LEDs and talk to clocks, you're going to use C. And when you start putting down like multiple processors on a programmable logic device and incorporating like system on chip concepts, those computers that are going to be on there, they're going to be programmed in C. Okay, so this is just the beginning. All right, let's talk about the anatomy. First, let's talk about the basic steps in here. Okay, when you create a C program, first step is you do what's called editing. This is where you're typing in the program. Okay, so you have an idea of what the program is going to do. That's kind of the design stage, but this is like you're physically implementing a program. You type in C. Okay, and it's the syntax that we're going to learn in this class. Okay, that's editing. You create, the output of that is basically a source file, which has an extension of .c. So we've seen that we've created these files already, like hello world.c. That's the source file. The next thing you do is you compile it. This is GCC, right? GCC is a compiler that takes your program, what you've typed, and it goes through and it checks to make sure you didn't type anything incorrectly. So you have to follow the syntax of the language. Then it converts your C code into the binary instructions, okay, for the CPU it's going to run on. Its output is called an object file. So your code becomes an object file, and it's like just a binary description of what you had. If you have errors in the compile, you go fix them. So you just go back and make sure that they're right, that you don't have any errors. Then what you do is the process called linking. So linking is where you bring in any other files that are needed for your program. Sometimes you have files that you created, like maybe you broke your program into multiple files, and you need to tell the main file where the other ones are. You also have built in what they call header files from C that allow you to bring in more functionality into your main program, and you have to bring them in. So you can specifically type them in your main program and tell the compiler, hey, I need you to go get this library and bring it in because I'm going to use some of the functionality in it. And then there's just flat out some files that you don't see. So when you install the C programming compiler, you install GCC, it knows some information about the computer, and when it takes your binaries, it actually puts some stuff around it to support having the operating system actually call your file, know where your file is, know where your program is, and how to elegantly exit it. So there's more that goes on. If you looked at the ones and zeros of what your compiled executable is, it's got more stuff in it than your syntax, and that's put in there by the GCC linking stage. The output of that is an executable file. So that in Linux, we have just a file without an extension. In Windows, you usually see the .exe extension, which stands for executable. Okay, we have not even talked about running your program yet. So at this point, you finally do what's called executing it. And that's where we do the ./ and then you type the name of the executable in Linux and you run it. And this is where you finally get to see, did it even do remotely what you thought it was going to do? And you just spend time going over and over and over and getting it to perform the way you did. Okay. So those are the steps when you create a C program. All right, let's look at the anatomy now. So here is a C program. This is just a silly one I wrote up, but it does have kind of the main blocks that you'll see in every C program. First and foremost, let's talk about comments. Comments are text that exist within a program file that are meant for a human to read to understand what's going on in the program. They are not interpreted by the compiler. The compiler completely ignores them. Okay. And this allows you to have readable code that somebody else can actually look at and understand. When you start a C program, you always put what they call a comment header at the top. And this is going to be the first thing that someone looks at when they open your program file. It's got a description of what the program does, who wrote it, when was it written, was it for a specific class or purpose, or was it for a specific class? And then what was the purpose? Like, what is this doing? Right? So this program illustrates the anatomy of a C program. Okay. So I know immediately without even looking at the code what this thing's doing. But you can also have comments throughout your code. Okay. And in C supports two primary types of comments. One is called a multi-line comment. And the way you do that is you put a / star or asterisk and then an asterisk / Everything between them is considered a comment. In this example that I'm pointing to right here, it's on one line, but if you look up here, this comment header was also a multi-line. So notice that I started the comment with this / asterisk, and then I ended it over here. Everything in between was treated as a comment. Then if you just want a single line comment, you just put / and everything after it until the end of the line is considered a comment. Okay, then you move on to what's called the preprocessor section. The preprocessor section provides additional information to the compiler that is separate from your main program, but it's going to be used by your main program. And where this goes is, if you look down here, we're going to have this thing called a main program. We'll cover that in a second. But before the main program, main function, and after your comment header is going to be the preprocessor section. Within this preprocessor section, you are going to have the ability to, number one, include other files. So we'll learn all this syntax later, but I'm just going to kind of, I'm showing you real syntax. So you have #include, which just is how you link to, or how you grab other files to be included in this program. You can create your own files, Or a big powerful part of C is that it provides a huge library of files that already have these pre-written functions for you to use. And that's where the power of C comes from, because people have already developed tons and tons of functions and they've tested them and they work, and you're going to be using a ton of these in this class. You can also define what we call macro substitutions. So let's say that you had a number called endpoints, and it was going to have a value of 10. And you're going to use that like in 20 or 30 different locations in your file, but it never really changes. Well, it's always a bad programming approach to hard code numbers throughout your program. And so you could make it a substitution where you could use a pound define and say, anytime you see endpoints, go ahead and replace it with 10. Notice that that's not compiling. Compiling is the act of converting your statements, your C program syntax, into executable or into instructions. This is something that happens before you compile. You just go through your program and you substitute the number 10 anywhere endpoints is used. That's why you call this a preprocessor section. Okay, another thing you can do is you can define functions. And a function is basically a little chunk of code that you're going to use over and over and over. So instead of just writing it over and over and over, you write it one time and then you call it from your main function. Okay, so that's the preprocessor. Then you get to the main function. Okay, all C programs have a main function and the name of it is main, M-A-I-N. You cannot change it. It is not allowed. The compiler looks for main. That is a keyword. Okay, so if you look at the main, you don't have to know this yet, but just to tell you what these things are, you have the function name main, and then you have on the left what is going to be returned by the function. It's kind of like the outputs. Okay, so when it's done, main completes and says, here's your output. And it's int stands for integer. It means it's going to give you back an integer. Then you have in the parentheses, what are the inputs? So if you're going to pass anything to main, you'd put it in this little parenthesis area here. Void means nothing. So the main function in C, you don't pass it anything, but you actually do return something, and we'll look at that in a second. Okay, after that, curly brackets. Curly brackets are how you tell a function is going to start and stop. So when you look at the main function, you're going to open a curly and you're going to close a curly. Everything else is within the main function. Okay. Good programming practice is not to start a new line with a curly bracket. So you always put the curly bracket after the name of the function and its input arguments. Okay. That's different than you'll see in the book, but the book was a little old. And so this is kind of the way that real programmers do it. Okay. All right. Then within the main program are functions and statements. Okay. A statement ends with a semicolon, and that's how C knows that it's over. So you can have statements that go multiple lines, but the compiler recognizes that the statement's over once it sees a semicolon. Within main, you can set up variables to reserve space in memory, give them a name, give them a number. You can make assignments to the variables, bn equals 109, and you can also call functions. So you can call functions, like in this example, we're calling this function up here. We're also calling a function that is defined in one of these include files. Okay, so that's all the stuff that sits in main. And at the end of main, you're going to have this statement called return. And this tells you what the program is going to return when it's completed. And in this situation, you always return 0 out of main. And that is because when the operating system runs main, when you type // and then whatever it is, it gets in the preprocessor stuff, it runs main program, and then it ends. You return to the operating system the value 0. That means that everything was okay. It's like I'm done and everything okay. You can have other return numbers, but usually they're automatically generated when something bad happens. Okay, and so you don't want to do that. Okay, all right. One of the things that we do to make it readable is we indent statements so that it's easy to see what goes with what. So an indent is usually a tab or 4 spaces, but notice that we'll have like the function int main void over here, and then I'll go in 4 spaces, and then I'll have this stuff. And if you had like another, let's say you did an if statement, which you'll learn about later, you'd say if this, and then underneath it, you'd tab in 4 spaces, and it just makes it very readable. Okay. All right. One of the last things is local versus global. Statements within a function encapsulated in a curly bracket and variables are only seen by that particular function. If you put them outside of main, then they can be seen by other things. So this function right here could be called by other functions. However, it also has curly brackets. So when you set up a variable inside of it, it only sees this variable, we'll call it sum, is only seen within this function. So this variable sum is not seen within main, as is a and b and s out are not seen within this function. So you encapsulate it, and that's called a local variable. But you could also throw a variable up here if you wanted to, and that would be called a global variable. Okay, that is the history and the anatomy of C, and we are now ready to start coding. All right, see ya.